Have you ever stopped to wonder what's actually going on inside of an AI like ChatGPT? How does it just get what you're asking? Well, today, we're pulling back the curtain on the engine that's driving this entire AI revolution. We're talking about the transformer architecture, which all started with a landmark 2017 paper called Attention is All You Need. But before we can get to the transformer, we have to grapple with a much more fundamental question. How does a machine, a thing of logic and code, possibly understand the messy, nuanced, and often ambiguous world of human language? For us, it's second nature. For a computer, well, figuring out context is an absolutely monumental challenge. I mean, just think about a simple word like mole. If you hear an American shrew mole, you picture a little animal. If you hear 1 mole of carbon dioxide, you think of chemistry class. And a biopsy of the mole means a skin growth. The words around it give us all the clues we need, but a computer doesn't have that intuition. How does it know which mole is the right one? Now, the old way of trying to solve this with models like recurrent neural networks, or RNNs, was to read a sentence just like we do, one word at a time, in order. The problem? They had a terrible memory. By the time an RNN got to the end of a long paragraph, it had often completely forgotten the crucial context from the beginning. It was like trying to follow a conversation but only remembering the last 3 words someone said. It just wasn't going to work. So, if that sequential approach was a dead end, how did transformers finally crack the code? Well, it all starts with a totally different way of thinking about language. It starts by turning words into numbers. The technique is called word embedding, and it's a fascinating idea. Essentially, every single word gets converted into a long list of numbers, what we call a vector. A better way to think about it is that each word gets a specific set of coordinates, placing it on a massive, invisible map of ideas. On this map, words with similar meanings, like happy and joyful, are located really close together. And here's where it gets kind of mind-blowing. You can actually do math with the concepts on this map. The most famous example is this one. If you take the coordinates for the word king, subtract the coordinates for man, and then add the coordinates for woman, you land almost exactly on the coordinates for queen. This showed us that complex relationships, like gender or even a country and its capital, could be represented as simple directions in this space. But, okay, there's a big catch. These word embeddings are static. They're fixed. The coordinates for the word track are the same whether you're talking about a running track, a song track, or tracking a package. So even though we turned words into numbers, we still haven't actually solved that core problem of context. And that is the problem that brings us to the absolute heart of the transformer. This is the big idea, the mechanism that gives that famous 2017 paper its name, attention. This is what finally allows the model to look at a whole sentence and figure out which other words are most important for understanding the meaning of any single word. The best way to understand it is with an analogy. Let's say a word wants to understand itself better in the context of a sentence. First, it sends out a query, which is like asking a question. Hey, who in this sentence is most relevant to me? In response, every other word holds up a key, which is like a label that advertises what it's about. The model then calculates a score to see how well each key matches the query. And finally, the words with the highest scores get to pass their value, their actual meaning and information, back to the original word. Okay, let's make that real. Look at the sentence. The cat didn't chase the mouse because it was not hungry. How does the AI know what it refers to? Well, the word it sends out its query. And when it compares its query to the keys of all the other words, look what happens. The word cat gets a massive attention score, 0.65. This is the AI's aha moment. It tells the model that cat is the most important piece of context for understanding it. The link is made. So that's the basic idea of attention. It's how one word can look at all the others and find its context. But a full transformer model doesn't just do this once. It scales this whole process up to build a really deep and nuanced understanding of language. It does this using what's called multi-head attention. You can think of it like having a whole team of those librarians working at the same time, in parallel. Each head, or each librarian, specializes in looking for different kinds of relationships. One head might focus on grammar, another on finding synonyms, and maybe a third is trying to figure out cause and effect. By running them all at once, and for context, GPT-3 uses 96 of these heads. The model builds this incredibly rich, multi-layered picture of the text.
All of this, the multi-head attention mechanism, gets bundled into something called a transformer block. Now, after attention has gone out and gathered all this rich context, the new context-aware information is passed to a feed-forward network. You can just think of this as a processing or thinking step. It's where the model digests what it just learned. And there's one last clever piece called a residual connection, which basically adds the original input back in, acting like a safety net to make sure no information gets lost as it flows through many of these blocks stacked on top of each other.
So, okay, we've got the blueprint for the machine. We have word embeddings, attention, and these transformer blocks. But why did this specific design trigger the AI explosion we're living through right now? The answer isn't just about the clever architecture, it's about pure, raw efficiency. Here is the absolute secret sauce, the real game changer. Unlike those old RNN models that had to read one word at a time, a transformer can calculate attention for every single word in the text all at once. This ability to do everything in parallel makes it a perfect match for modern computer hardware, like GPUs. And that meant researchers could suddenly train models on a scale that was simply unimaginable before. And when I say scale, I mean it. Because this parallelization unlocked the ability to build models with a truly staggering number of parameters. The GPT-3 model, which really kicked off this current wave, has 175 billion tunable parameters inside of it. That number is a direct consequence of the transformer's design. And this chart really puts that number into perspective. You can see the older models down here with parameters in the millions. Then you get the first transformers, which jumped to the hundreds of millions. And then this astronomical leap to 175 billion with models like GPT-3. It's just a completely different league. And that massive scale is where the magic really happens. And so that brings us right back to the beginning. It's this beautiful combination, turning words into numbers with embeddings, using the powerful attention mechanism to understand context, and then leveraging parallelization to scale it to billions of parameters. That is the engine, the fundamental architecture, inside the tools like ChatGPT that are changing our world. The attention mechanism was the breakthrough that took AI from just processing sequences of words to truly understanding the relationships between them. It was a leap from pattern matching to context. And it makes you wonder, what's the next great leap? What will be the attention mechanism for something even more profound, like genuine reasoning, or maybe even one day consciousness? That's the question that will drive the next generation of AI.